Hello everyone, I'm Alsaati and today I'm going to share with you some of our recent effort toward enabling an embedded immersion cooling for thermal management of heterogeneous packaging. Digital transformation, mobility, and connectivity are expanding into new markets, while technologies are converging to bring more and more applications into smaller, smarter devices with increased performance and smaller form factor. In doing so, more heterogeneous integration packages are anticipated in the near future. And there are several added values that heterogeneous integration can add, such as small form factor, higher performance, and faster time to market to lower cost and increase flexibility. But how would heterogeneous integration affect the thermal design of the package? It's nothing new, and we have known for a long time that hotspots on devices ultimately cause throttling and limits reliability. Stacking components vertically only worsen the hotspot challenge for internal components. As we start to intermix multiple components, the thermal crosstalk between these components is now an increasing challenge. Furthermore, many of the applications that are being served are increasingly dynamic, where power generation not only transient temporally but also spatially. These challenges can potentially be addressed locally by embedding a thermal solution inside the package along with all other components. There are thermal implications that need to be considered as we design an effective embedded thermal solution along with other devices. For example, a temperature gradient of 5 degrees can degrade battery performance. In addition, different components within power electronics in close proximity can differ in temperature limits up to 125 degrees. In this case, an embedded heatsink might be desirable. On the other hand, FPGA power maps are dynamic by design, which calls for an adjustable thermal resistance map to reduce thermal-induced fatigue. In fact, an effective thermal management is crucial for signal integrity. Photonic devices can have high dynamic power density, and the thermal challenge associated with such devices is to dampen the temperature fluctuation. It has been reported that a temperature swing of 10 degrees can shift signal frequency up to 1.2 terahertz. Similarly, MEMS resonance frequency is highly sensitive to temperature fluctuation. Based on those implications, an adjustable thermal resistance is advantageous to stabilize temperature across the electronic package. Now let's take a closer look into the heterogeneous packaging from a thermal perspective. The thermal resistance network shown on the left represents the heterogeneous package where the nodes are the power generation components. Multiple thermal interfaces within current packages hinder the spreading of internal hotspots. Skipping all the interfaces and dissipating the heat through an embedded immersion cooling is advantageous for volumetric scaling of heterogeneous packaging. Not only that the two-phase thermal resistance associated with boiling is relatively low, it is also providing a variable thermal resistance that get adjusted based on the magnitude of the power generated locally. This feature helps maintaining isothermalization across the diverse components with various power generation profiles. In other words, the inherent self-adjusting thermal resistance limits the thermal crosstalk. However, in order to enable such technology, it's crucial to have a, a concrete understanding of the effect of extreme confinement on boiling and develop a predictive model to guide and optimize thermal designs. To gain a deeper understanding of the extreme confinement effect on boiling, we use the confined boiling facility shown here. The facility enables the measurement of boiling surface temperature and heat flux. As illustrated in the schematic drawing, the facility features an adjustable optical transparent window to control the confinement gap and the confinement diameter above the boiling surface. The facility is also equipped with a high-speed camera to capture the two-phase interface dynamics through a rigid borescope as boiling takes place. And I would like to acknowledge Professor Tim Fisher and his colleagues for their contribution in the facility development. This graph shows the experimental boiling curve obtained for confined boiling. For comparison, the unconfined pool boiling curve is included in the graph as the blue line. We also use the dimensionless bond number to normalize the confinement gap by capillary length of the working fluid. As you can see, we observed that for lower heat flux values, the surface temperature is lower for confined boiling compared to unconfined boiling. However, the dryout limit for confined boiling is significantly lower than the dryout limit of pool boiling. Like unconfined boiling, heat is dissipated through natural convection at low heat flux values, where no nucleation sites are activated. On the other hand, at high heat flux conditions, heat is dissipated through phase change and vapor bubbles are generated at high frequencies. In these conditions, the liquid wetting rate is insufficient to re-wet the entire surface, resulting in partial dryout of the boiling surface. In between natural convection and partial dryout regime, the boiling exhibits time periodic oscillatory behavior. In this intermittent boiling regime, vapor is generated slow enough that the entire boiling surface is able to re-wet. Now, what's interesting is that in the case of unconfined boiling, increasing heat flux activates more nucleation sites, which results in increasing the heat transfer coefficient. However, in confined boiling, the highest heat transfer coefficient occurs at the intermittent boiling regimes, where higher heat flux condition where increasing the heat flux condition further lowers the heat transfer coefficient. In fact, confined boiling features unique phenomena that influence the heat transport within the package. One of those unique phenomena is the nucleation enhanced wicking. Those images illustrate a time series of vapor generation, starting with a partially dry surface at T1. Capillary wicking reduces the fraction of dry area within the confinement space, as shown at T2. Then, as liquid wets relatively hot, dry surface, nucleation occurs on the wetted region. And due to the phase change volumetric expansion, liquid get displaced to the dry region, as shown at T4, and continue doing so in a repeating cycle. This mechanism improves the re-wetting rate of boiling surface, which results in an improved heat transfer coefficient. Another enhancement mechanism is the fact that confinement wall forces a vapor bubble to grow parallel to the boiling surface, which spreads the liquid layer thinner, forming microlayer on boiling surface. As a result, confined vapor bubbles have larger microlayer area compared to the unconfined case, where bubbles can freely depart from the boiling surface. This mechanism also enhances the heat transfer coefficient due to the larger microlayer area. Steam bubble boiling is another unique phenomena that is uniquely observed in confined boiling configurations. The time series in Figure A demonstrates a life cycle of confined steam boiling. As the trapped bubble expands and reaches the confinement edge, liquid replaces the escaped vapor at various re-wetting rate. Viscous resistance slow the re-wetting of the regions furthest from the confinement edge, which result in splitting of the trapped bubble. Then new vapor bubble stems from the trapped remaining of the escaped bubble. Compared to vapor embryo at nucleation sites, the relatively large radius of the trapped bubble allows for phase change to occur at lower superheat. The graph here illustrates the enhancement in heat transfer coefficient of confined boiling. The newly observed stem bubble boiling dominates the thermal transfer enhancement in extremely confined configuration, where the gap size corresponds to a bond number less than 0.3. However, for moderately confined boiling, stem bubble boiling enhancements diminishes, and the enhancements observed are limited to the nucleate-based boiling enhancements. In summary, two distinct confined boiling regimes are identified, namely intermittent boiling and partial dryout regime. Also, confinement improves the heat transfer coefficient through enlarging the evaporative microlayer area, and nucleation enhanced wicking for moderately confined configurations. Stem bubble boiling further enhances the heat transfer for extremely confined boiling. This deeper mechanistic understanding of the differences between confined boiling and pool boiling is crucial to design and optimize an effective embedded immersion cooling solution. This understanding also motivates development of a new modeling framework for confined boiling. The classical static framework assumes uniform boiling system states, temporally and spatially. This assumption conflicts with the observed hysteresis, intermittent activity, interactions between nucleation sites, and the sensitivity to initial conditions. Rather, a nonlinear chaos dynamic framework has the potential to fill this gap and better suited to model confined boiling, where an improved theory can be developed based on the mechanistic understanding of the confined boiling and provides a probabilistic prediction of the system states. With that, I would like to thank you for your time, and if you have any further questions, please contact me through email.